Hello class, welcome to section 2.3. We're going to focus on set operations. This means working with operations such as union, intersection, complements, and then how they affect sets and then the components of those sets. So first, some definitions. The universal set, again, is a general set that contains all elements under discussion. So for example, in a class of 20 students, 9 men, 11 women, the universal set is the entire class, and the men and women are two individual sets. And we can represent that with a Venn diagram. Venn diagram, for those you may remember, is a visual representation of sets, such as what's drawn here. So I have C, the class being my universal, and typically the universal, when you draw a Venn diagram, is represented by the rectangle surrounding everything, because that encompasses all possible sets. So we have, then within those sets, we have men and women. And they'll be considered two disjoint sets, sets that have no overlap. So again, disjoint sets have no intersection. And going back to what we went over in section 2.2, a proper subset is represented as you see here. And we said a proper subset is a set that is, think of it as less than or equal to, has all the elements of another set, or all of its elements are included in another set, but that they're not the same set. So for example, the set of men is a subset of the universal, a subset of the set of class. And it's represented, a proper subset is represented by, in the Venn diagram format, is what you see here. So here A is our integers, B is even positive integers. So again, all even positive integers are included in the set A integers, but they're not the same. And that's what makes a proper subset different than a regular subset. Equal sets in Venn diagrams represented as you see. And then sets that have common elements are represented like this, having a middle intersection ground. And the two of the important definitions that we use are union and intersection. Union is a set of elements when you consider two sets in set A, B, or both. So again, if you look at the second example here, the union is all the elements in set A or B, denoted as, denoted as A union B, what I've written down here. So for example, if we ignore a Venn diagram for a minute, and I say set A is defined as 2, 3, 5, and 9, set B is defined as 1, 4, 5, 9, 14, 20. Then A union B, as you can see, is represented with what looks like a U, a symbol for U for union. It's equal to, so again, union is a fancy way of saying that everything in both sets is included. So I'm just writing down everything that's in both sets. So I start with 1, then there's 2, then there's 3, there's 4 in B, then there's a 5 in both A and B. There's no 6, there's no 7, there's no 8, there is a 9. There's no 10 through 13, there's a 14, there's a 20, so I'm writing them all down. Again, there's every possible element that's in one or both of the sets. And you'll notice, even though I have two 5s and two 9s, I do not repeat them. And that's very important. Unions, you do not repeat numbers, no matter how many there are. So for example, set B, what is the union with the null set? Basically we're saying we're going to combine our set B with nothing else, so it's just going to be set B. And that's the truth for any union with a null set. So B becomes, B union the null set is just B again, 1, 4, 5, 9, 14, and 20. And to better illustrate how the Venn diagrams can work, this link will take us to a Venn diagram, or interactive Venn diagram, which allows you to play around. And let me install this. So here we have our it's a Java applet. It allows us to see and interact with Venn diagrams. Here's an example of two. So when we look at union, here's all the elements of my red circle, all the elements of my blue, my green, excuse me. And you can see here I selected and or. Or is commonly associated with union. So when we say this or this, it's referred to as it's referencing a union statement. So you say union includes everything in both circles. And as you can see here in the example drawn to you, or example I've drawn, it's the same idea. Intersection. Of course, everything that's common to both, represented A intersection B. With the what looks like an upside down U, think of it like an N for intersection to denote intersection. And again, this uses the phrase "and" in the description. So we say this and this is a way to reference verbally reference intersection. So, for example, if A is a set of numbers 1 through 8, B's numbers 3, 7, 9, 11, 12. So, what is A intersection B? And that's, what do they have in common? And in these two sets, they have in common only 3 and 7. And likewise, what is the intersection of A and the null set? In other words, what do they have in common? Again, it's going to be nothing. It's going to be the null set. You can see here I've drawn an example of what it needs to have two sets that are intersected. In this case, with A and B, it's the middle area between two. And if I look back at my graph, turn on and there again is the intersection between two sets. And this applet is nice because it allows you to play around it with the shading and understand how intersection, complements later on all work out. And since I brought it up, let's look at complement. A complement I like to think of this way. Of course, the definition is set A as a complement A prime. That's how it's read. The little apostrophe is read as prime. So we say A prime, which is the set of elements not in A but in the universal set. In other words, the best way I like to think of it is if there's a 30% chance of rain, what's the chance that it doesn't rain? It's going to be 70%. That's called a complement. So what's the chance of something not happening, for example? Or in the case of a set, a Venn diagram, everything outside the set that's being considered. So for example, if U is a set of numbers from 1 to 20, and A is a set from 2, 4, 6, 8, 14, 17, 19, I'll ask you to define A prime. A prime then is everything not in A but in the universal. So if you look at that list, 1, 3, 5, 7, 9, and so on, none of those numbers are in set A. Set A is 2, 4, 6, 8, 14, 17, 19. None of those numbers are in A prime. A prime is all the numbers that are not in A but in the universal. So in other words, if we're considering the universal for 1 to 20, we're excluding the numbers 2, 4, 6, 8, 14, 17, 19. So then what's left over? That's the complement. And in a graphical sense, on a Venn diagram, you can see that A is the white circle. A prime is everything outside that, but in the universal. And if I go back to my little applet here, then we go down to 1. So this is my normal set, and that's the complement, everything outside of the set. So again, here's my regular set, complements everything outside. And so let's continue. Just a couple more definitions to go over, and we'll see some examples. One is the difference of sets. Just like subtraction, as you might think, it's a set of elements. If I say the difference, and notice how it's written, the difference of sets B and A, remember B is first, is the set of elements in B but not in A. And since it's written with B first, it's thought of as just like saying B minus A. So again, it's a set of elements that are in B or in the first set mentioned, but not in A, and not in the second set mentioned. So for example, if I have a set of n is 2, 3, 5, 7, so on, E is a set of even integers, all the elements are in B, excuse me, in N, but not in E. That is 3, 5, 7, 9, 17. Operations on sets. Now we'll get on into this a little more in 2.4, but basically, operations on sets are going to be questions where I'll give you as you can see here, I'll give you sets A and B, and I'll say evaluate this intersection or this union. And the Morgan's laws are one of the ways that we can make things a little easier for us. The Morgan's law basically say that it's a way of thinking of complements. So, in other words, A intersection B, and I say prime, so I'm saying the complement of whatever A intersection B is. Another way of writing that is A prime union B prime. And below it you see, if it's a union, according to Morgan's laws, it's equivalent to say A prime intersection B prime. Now instead of, what I would recommend, instead of trying to memorize these specific rules, the way to think of it is, think of the prime as a negative number. And if you remember from algebra, when you distribute negatives, everything inside the parentheses takes on the opposite value. So, positive numbers become negative, negative numbers become positive, signs switch. In the same way, think of the Morgan law as distributing the prime. So if I distribute the prime to both my sets, A, which no longer has a prime, becomes A prime. B, which doesn't have a prime, becomes prime. And then the intersection flips and becomes union. And likewise in the second one, when I distribute my prime, A becomes prime, B becomes prime, and union becomes intersection. And here's some good examples to take a look at. So in the first one, A intersection B prime, and I say the prime of all that. So, and again, these are just other ways of writing it. Now you can do, and we'll see some examples, these problems the way they are, on the left-hand side. Sometimes, though, it's easier to apply the Morgan's laws because it gives you an easier operation to do. So in the first one, if I quote-unquote distribute my prime, A becomes prime, B prime becomes regular B, intersection becomes union. In the second one, A prime union B, if I apply the prime to all that, the A prime and prime, think of it like negatives canceling out. Negative times negative is positive, so A prime becomes A. Union becomes intersection, B becomes B prime. It's like saying B is positive, now B is negative. And the same for the last one. A and B are both prime, so they become just regular A and B. Union becomes intersection. So let's look at some more examples. Let me zoom in on this. So, as I said, a lot of this is how do operations work. And that's what this last part was. The general rule is work from the inside to the outside. So, for example, A is going to be 1, 3, 4, 5, 8, 10, 11, 12. B, as you can see, C is there. And then the union is 1 to, the universal is 1 to 20. All numbers between 1 and 20. So one question would be, what is A prime, B prime, and C prime? Just take a minute and finish that yourself. Now, if you've worked on that yourself, this is what you should be coming out with. A prime, again, all the elements that are not in A but in the universal are 2, 6, 7, 9, 13 through 20, really. B prime 1, 3, 8, 10, 12, 13, 14, 17, 18, 19, 20. And C prime is 1, 2, 4, 5, 7, 8, 10, 11, and then 13 to 20. And a lot of times when you do problems where you're finding, intersection of A prime, B prime, etc., it helps even if I'm not asking you specifically for A prime, B prime, and C prime, and so on, it helps to write them out. Write them out, have them in front of you so you can see. So you don't want to try to do too much mentally with a lot of these problems, especially the really complex ones, because it's going to be a lot of numbers to keep track of. It helps to write them down and have them in front of you so you can always see what they are. So here's some examples. With the sets given, I want you to try to find A union B, A prime union B, A prime intersection B, and so on and so forth. Now if you look at 8 and 9, you might think, well, how do we do this? We have 3 now. And it's very much like there is an order of operations, like we said, work inside to outside. I would recommend for 8, find what is the union of A and C prime. So go back to your lists. A is 1, 3, 4, 5, 8, 10, 11, 12. C is 1, 2, 4, and so on. Find that union first. Then that set, what is the intersection, it says, with set B compared to set B up here. And that will be your answer. Same thing with 9. I recommend find B intersection A prime first, then take the complement, or you can take the complement and say B prime union A. Either way, I'd recommend do this part on the left, that pair first. Once you have that, then find the intersection with B prime. So give yourself a minute and try that. Now if you put me on pause, hopefully, and then tried it, here are the answers you should be getting. And I'll try to go through these. So for number 1, we have essentially 1 through 12, and then 15, 16. Number 2, you can see, so on and so forth. Let me jump back up. Again, here's what we're looking at. A union B, A prime union B, and so on and so forth. And these are the answers for each one of these 9, and I'll scroll down just so you can see the rest of them. And like I said, with these, it's helpful to do it in parts. Let's do one, for example. Let's say, let's do number 7. Let's say, what is B prime intersection with C, and then prime that. Now you have a couple options. You can just use the Morgan's laws to rewrite that as B union C prime, or you can take what's B prime intersection C, and then take the complement of that. I'm going to find B prime intersection C first. So B prime is, we have this right here, and I intersect that with C here. So hopefully I have enough room. Let me do it right here for you. So, intersection means what do they have in common? With B prime and C, well, let's see. They have 3 in common. They have, don't have a 6. And then with the intersection, to speed things up, one of the quicker ways of doing it is find the smaller set. And since it's intersection, you know that the intersection has to at least have those numbers. So in this case, C is a smaller set, and let's just look for those numbers. There's 3, no 6, no 9, and there's 12. So we get that. Okay. So, now we have 3 and 12. Now it's saying, once we have that set, we take the complement of that set. So what is the complement of 3 and 12 given the universal 1 to 20? Well, it's every number in the universal except for 3 and 12. And if we look at our numbers, number 7, you can see that's why it's so long. There's every number in there from 1 to 20 with the exception of 3 and 12. And you can see there's between 2 and 4, 11 and 13, of course we're missing our numbers. And that's how we find these That's how we work these out. Again, you work from inside to the outside. Now lastly, as a transition to 2.4, we'll eventually be working with 3 Venn diagrams. Here's an example right here. And I labeled each section. Now this isn't a rule, the way I labeled it. I just happened to do it from left to right. Just to distinguish, what is what. So section 1, Roman numeral 1, is everything in A, but not everything else. So you can see that the intersected sections, there are 3 of them, that A intersects with both B and C. There's 2, 5, and 4. Each of those represents its own small section. So let's use this to think of how we do intersections. Which regions are represented by A intersection B union with C? So again, work from the inside out. So we'll start with the parentheses. Where can we find A intersection B? What regions are represented by A intersection B? We'll start with that. Here's A and B, of course, the top 2 circles. If it's just them, that middle section is, of course, right here. And that's represented by the 2 regions 2 and 5. So we're starting with that. So we say, so far we have 2 and 5. We want to find the union of that with all of C. Remember, union means everything combined. So since we're combining everything, automatically we know that we're going to have every region in set C, which is 5, 4, 6, and 7. And obviously the order does not matter the way I'm writing this. Now if we combine that with everything in the intersection of A and B, that's 2 and 5, there's an overlap. We already have 5. We don't need to write it again, which means we just include 2. Now, if we look at the next question, which regions are represented by A union C intersected with B union C? So we have 4 parts now. Again, do them individually. We'll first do A union C. Let's find out what regions those are. Then let's find B union C, find out what those regions are. Then we'll find the intersection of those 2 regions. A union C. Between those 2 circles, that middle section is represented by regions 4 and 5. B and C, represented by 5 and 6. So in this case, what regions are represented by A union C intersected with B union C? Again, let's write them out. A union C includes the regions 4 and 5. B union C includes regions 5 and 6. Since we're talking about intersection, what do they have in common? They both have the 5 in common. So that is our answer. Region 5. That is going to be their intersection. Now, a lot of problems like this, you're going to be asked is there a conclusion that can be made? And in this case, all we can conclude is that A and B, the sets represented by those 2 questions, have an intersection of region 5. So a question like this just mainly is asking 3 things. Is there a particular union? Is there a particular intersection that is notable? Or lastly, are they the same regions? And of course, in this case, they're not the same. The only thing worth noting is that they have an intersection in section 5. So this concludes section 2.3. Yeah. As always, if you have any questions, feel free to contact me and have